The last topic we're going to look at for spherical mirrors is magnification. So, what magnification is the relationship between the distance from your center line to where the light comes from. That's called your object height. The relationship between that location and the location of where the image is. So, we will end up normally defining the object height to be positive. So in that situation, we lock in my coordinate system that's my positive direction in that sense. So if I have an object height, if I have an image height that's also positive, then it will end up pointing in the upward direction. It will end up appearing above the center line. If I end up having a negative image height, then it will appear to be below the line. And notice in this situation, if it goes from here to there, it will also be upside down. So we'll end up seeing that in a moment. The magnification then, in terms of notation, it's the quotient of the image height divided by the object height. So it's so if the magnification is positive, is bigger than 1, if your image distance is this, then the object is this, the image is that. So it looks bigger, which is what we normally think of when we think of magnification. It's larger, and it's the factor by which it appears to be larger. Geometrically, again, the geometry is shown to you in your text. I'm not going to try to end up showing you the geometry of where it comes from, but it will end up being the negative of your image distance over the object distance. So it's not positive, it's minus your image distance over the object distance. So there's a few things that ends up telling you. If your image distance is positive, your object distance is always positive, then your magnification is negative. Whereas if your image distance is negative, then your magnification will be positive. So in terms of understanding that geometry I was telling you about before, putting it into other types of words, if the magnitude of your magnification is greater than 1, then it looks bigger. The image is larger than the object was. If magnification magnitude is absolute value is less than 1, then it will look smaller. If your magnification is positive, then it will appear to be on the same side, whether it's bigger or smaller. So it will end up appearing upright. So if you had one that's further up, then the image would appear further up. Whereas if your image was below and it was even from a higher point, then it would look even further down. So it will look upside down if your magnification is negative. So as a final sort of example of this, we can see how a flat mirror ends up being a special case of this. So if you end up where we talked about, some things about radius of, when we go around a turn in a car, that a small radius is going to be where it's strongly curved. The bigger the radius is, the less curvature you get. So if you had something that was perfectly flat, then that would end up being a radius of infinity, either positive or negative. And mathematically, we'll see it doesn't matter which one. So your focal length is infinite for a flat mirror. In terms of thinking about this, you've got light that comes from infinitely far away, comes into there. It doesn't go into anywhere either side. It just bounces back from all the different points on a flat mirror. So in order to make sure that makes sense geometrically, and also this shows at least that mirror equation sort of makes sense geometrically, that the reciprocal of the object distance then for a flat mirror plus the reciprocal of the image distance will end up being 1 over infinity, which is 0. So your 1 over your object distance is minus 1 over your image distance. So your image position is equal to the negative of the object position. So in a flat mirror, the object appears to be exactly as far behind the mirror as the object was in front of the mirror. So, and again, that's what you expect with a flat mirror. And your magnification, when we calculate that, we end up with a magnification of 1, which of course a flat mirror looks like it's the same size. So again, that doesn't prove that that's the right formula, but at least it makes sure that in that special case, that makes sense, and that it is in fact generally true. Finally, we'll end up taking a look at some preliminaries for what the next one is. And whenever you have, so we've talked about now with reflection, we've talked about what happens when light hits something and bounces back. When light hits a surface, it could do one of 3 things. The surface could absorb it. We're not going to worry a whole lot about that. In some ways, that's more chemistry than it is physics. That you can account for it with some other stuff we're not going to do in this course. It could reflect, which is what we just got through talking about. Or for some materials, the light may pass through. So that's what we're going to be looking at next. What happens if light ends up going through an interface between 2 surfaces? And in terms of understanding what happens whenever light that's moving through one region ends up coming to another region. What happens is, as the electric field is oscillating whenever it comes in and hits, the electric field is causing the electrons on the surface to wobble back and forth, because of course, remember, force equals Q times E, so your electric force is going to be bobbing the electrons back and forth. And so then, whenever this basically continues to transmit it further back, that if the electric field is pointing in one particular direction here, it's pointing the same direction back behind it. So how often, how often this wiggles on this side has to match how often it wiggles on the other side. And how often it wiggles is, of course, the frequency. So the frequency of the light on one side of it has to match the frequency on the other side. However, whenever light ends up passing into some kind of medium that's not a vacuum, that the speed of the light will be smaller than the speed of light would be in vacuum. And the amount by which it's smaller will end up being called the refractive index of the medium. So the speed of light inside of some other medium will be the speed of light in vacuum divided by your refractive index. The refractive index in general does depend on the frequency of the light. We'll talk about some consequences of that. But that's going to be the focus for our next thing. And in terms of looking further out, I'm going to try to get everything I need on refraction and thin lenses in the next lecture, which will then reserve the rest of the course for talking about nuclear reactions, which is, again, a totally different nuclei and nuclear reactions, which is a really very different topic, but one that we also need to end up covering this semester. All right.